So simplicial complexes are very nice, but they are too rigid a structure which forces us to take, for example, if we took a torus and tried to make it into a simplicial complex, we can take the torus with its usual identification, but we'll have to subdivide it a lot. We'll have to break it up into a lot of triangles, 7 of them in fact, to make it into a simplicial complex, which is a nuisance. So there are various looser notions which are often called triangulations, which are used to replace say simplicial complexes when you really want to avoid having too many simplices, both for practical reasons but also for a conceptual reason that you want to say that things can be simplified unless obstructed by algebraic topology, kind of a version of Whitehead theory. And with simplicial complexes you always have purely combinatorial obstructions, not topological ones that come in. So, well, fortunately Hatcher, because his book is so standard, it has one version of this has become standard, which is a delta complex. And for the case of the torus, it's this diagram, and we take VV, VV here, and let's give these guys names, alpha, beta. We call this alpha, beta. The edges are alpha, beta, and there is a third edge, which is gamma. Okay, which we can look at as having two different simplices and making a bunch of identifications. Yes, so we identify, well, this guy with this guy, this guy with this guy, and the middle one with the middle one. Okay, so delta complexes, these are obtained, and we can just assume finite, since our goal anyway is one where we don't need to deal with infinite. This will make both topology and orientation simpler, and in the case of topology I won't say anything further because there is only one reasonable choice for topology in the finite case. So and this is finite, so we start with disjoint union of simplices. So simplices here means delta n for some n. Yeah, remember we wrote these as these. Okay, so these simplices have faces, but delta n is also the geometric realization of 2 to the power of the set 0, 1 to n. So it is also a simplicial complex, and it's a geometric realization of this. So a face is a subsimplex, simplex in delta n. Okay, and then we take the quotient, a delta complex is given by, well, of course, a collection of simplices and collections of identifications. So collections script f alpha, so alpha in A, with f alpha being the collections of faces of the simplices. Now given two faces, but here faces of two simplices, and maybe instead of inserting, let me say this. So the faces, but we have further with vertices ordered. Okay, and then so when we have faces or vertices ordered, we have linear maps between faces of the simplices with vertices ordered and all of the same dimension. For fixed alpha. So for a fixed alpha, well, we can have some identifications between vertices, some between edges, some between triangles, etc. Many different sets of edges identified. But for any given f alpha, we cannot identify an edge with a vertex. So for any fixed alpha, we have a specific number, you can call it whatever, d alpha, of d alpha. And for fixed, every element in f alpha is a face of dimension d alpha. Different alphas can have faces of different dimensions. So we have linear maps between faces in F alpha. Why is that? Because as soon as I have two simplices and I have ordered their vertices, so this is V0, V1, V2, and this is W0, W1, W2, you immediately have a canonical linear map sending the first one to the first one, the second one to the second one, the third one to the third one. So we have linear orders, we get linear maps, we quotient by identifying using these. Okay, this is a semi-formal definition of what a delta complex is. With a little work, you can make it fully formal. You can write it out. So what we have is the following. We start with simplices. I'm just going to take finitely many, all of various dimensions potentially, and we're going to glue. And the way we glue is we specify bunches of gluings. So at this edge, and this edge may all be glued together. Then they should all go into the same F. And we order these vertices. We specify the order of the vertices when we are writing them in F alpha. And we identify this together by the linear maps corresponding to the order. The result is what is called a delta complex. Okay, so we can define simplicial homology for these. So we can orient simplices. You have to be a little bit careful here, but since these are finite, it's not difficult. There'll be certain maximal faces which are identified together and everything. So pick those maximal faces and orient them. Orient one of them and make the others inherit that orientation. And then you make it, everything smaller than that should also inherit orientations from the outer gluing. And then you get an orientation on the vertices as well. Okay, so I said this carefully because, for example, in the torus we ended up with just one vertex. Okay, and so now given this, there's not the details are all very similar. So let's instead just work at an example. Okay, we can still define homology. The chain complex and homology. By the way, I should comment here that the chain complex is an algebraic object in its own right. It's a collection of R modules which are free together with a boundary map with del squared equals 0. When you see more sophisticated algebraic topology, you think of this as two steps, going to chains and going to homology, and the intermediate thing is also of interest. So anyway, so here we have alpha, beta, as I said gamma. This is also beta, so I should clarify by putting it into, and this is also alpha. Okay, so this is a simplex. This is a delta complex for the torus. Okay, so let's now look at what this is. Remember, this is V0. Sorry, you could just call it V because these are all V. Okay, so C0 is Z, and I can write it as Z generated by V. How about C1? C1 is Z cubed, it's isomorphic to Z cubed, and it is Z free abelian group generated by alpha, beta, and gamma. How about delta 1? You can see delta 1 is identically 0 because the boundary of alpha is V minus V, boundary of beta is V minus V, boundary of gamma is also V minus V. Okay. How about C2 now? C2, there are two different simplices. Let's call this T1 and T2. Okay, so C2 is Z of T1, T2. And let's look at the boundary map. Boundary of T1 is going to be, let's say, assume it's been oriented as you would expect from the picture. That is alpha, beta, and then gamma. So the boundary of T1 is going to be alpha plus beta minus gamma. And how about boundary of T2? This is going to be equal to, well, you write it as beta plus alpha minus gamma, but this is also boundary of T1. Okay, this is wonderful now. And C3 is 0. So let's calculate the homology here. So let's just do it on this side. So what is H0? H0 is kernel of delta 0 divided by image of delta 1. Now kernel of delta 0 is the map which is 0 map, so it's all of this which is Z. How about delta 1? Delta 1 happens to be a 0 map, so this is a by 0 group, so this is Z itself. H1 is the most complicated, so H1 is kernel of delta 1 by image of delta 2. In this case there is both a kernel and an image, so kernel is everything. So this is Z of alpha, beta, gamma, and I can say it's the quotient by the single element which is the boundary of T1, which happens to be the same as boundary of T2. So the image is this, and this you can see is isomorphic to Z of alpha, beta, because gamma can be written as in the quotient, gamma is a linear combination of alpha and beta, and there's no dependence among alpha beta. Any linear combination of alpha beta which is a multiple of this must be 0. So this is isomorphic to Z of alpha beta by the quotient map which sends gamma to 0. So H1 is isomorphic to Z squared, which was also pi 1. In general, H1 will be the abelianization of the fundamental group. And how about H2? This is going to be kernel of delta 2 by image of delta 3. There's no delta 3, so it's just going to be kernel of delta 2. But you can say T1 and T2 don't go to 0, but their difference goes to 0. And since they go to torsion-free elements, this is exactly the group generated by the difference. And that is isomorphic to Z. Okay, so my purpose of looking at delta complexes, which you can see in more detail, say in Hatch's book, was merely that we can make these kind of calculations in a little bit of a compact fashion, and also illustrated case where we had both kernel and boundary, image of boundary, without having endless proliferation of indices.